Okay, yesterday we will discuss about the properties of the lasers. Okay, today we'll discuss Einstein coefficient. Einstein coefficients. So Einstein proposed some theory for explaining the this emission, absorption, dissolve process. So he also proposed some coefficients also. So for explaining the absorption and emission process. Okay, so we will discuss about the those coefficients and relation between the those coefficients we will discuss today. Okay, yeah. So yesterday we will discuss about the properties of the characteristics of the laser. Okay, in that so mainly we are discussing about the four characteristics of the laser. Okay, now so Einstein quantum theory for radiation. So in 1917, Einstein proposed a mathematical expression for the existence of stimulated emission of light. The theory is known as Einstein quantum theory of radiation. Already we discussed in last class. So if electron is coming from higher energy state to lower energy state, what happened? Emission will be takes place for that emission. So for explaining the energy of that emission, so Einstein proposed one equation that is equal to, so E2 minus E1 is equal to h nu. Okay, so that is the expression, so Einstein expression for the emission process. Similarly, absorption process also same. Whenever it absorbs the amount of h nu energy, okay, it will goes to the so lower energy state to higher energy state. Okay, that is the Einstein absorption expression. So both are same only here. Okay, now here from the theory of interaction of radiation with matter, so considering two level energy system, let n1 and n2, yeah, so here we are taking two level energy systems for explaining the so interaction of radiation with matter, interaction of radiation with matter. So for explaining that interaction with radiation of matter, we are considering two energy levels, two energy levels. Those energy levels are just, see here I am taking here two energy levels. So one is the E1 energy, see one is the E1 energy level. So here this is the E1 energy level, and next one is the E2 energy level. So this is the E2 energy level. Okay, here N1 atoms will be present in E1 energy level. Similarly, here N2 atoms will be present in E2 energy level. Okay, E2 energy level. So let us consider, so this is the ground state is E1 energy level. Here number of electrons, here we are discussing about the electrons now. So number of electrons in a ground state equal to N1. Similarly, so this is the excited state. This energy level we are mentioned here E2. Okay, this is the E2 energy level, E2 energy level, and here number of electrons present in a excited state is so N2. Okay, so now we are discussing about the when absorption will be takes place, when emission will be takes place. Okay, so absorption, first process is absorption. So absorption means when radiation is instant on the, see here, so that means photon, number of photons are instant on the ground state energy level, ground state energy level. So those photons are absorbed by the these ground state, these ground state electrons, absorbed by these ground state electrons, and these ground state electrons will goes to the excited state, ground state electrons will goes to the excited state. That is depends on the density of the photons. So how much energy, that means density, how to calculate the energy density of the photons. Energy density means here, so each photon having energy here h nu energy, each photon having h nu energy. So here number of photons, so if you will take, there are a n number of photons are there. So n h nu is the energy density, n h nu is the energy density. Okay, so that means here absorption, absorption is depends on the, so main here two parameters. So one is the energy density of the so this photon, interacting photon, here photons are interacting with the ground state energy, ground state energy level, photons are interacting with the ground state energy level. That's why, so energy density of the interacting photons, So that means here number of atoms will goes to the excited state is depends on the, so two parameters here. One is the, so I will explain you here. Yeah, so N1 be the number of atoms per the unit volume in energy level E1, N2 be the number of atoms per uh, unit volume with energy level E2. Okay, so already we discussed here. So N be the number of photons for unit volume at frequency nu, such that so H nu is equal to E2 minus E1. Okay, therefore photon density is here. So photon energy density is how much here? So rho of nu. So here rho gives the energy density rho of nu. Nu is the here photon frequency. Okay, now h nu is the energy of the each photon. Here total n photons are there, so energy density will be so nh nu. Yeah. So when these photons interact with atoms, so here two cases. So upward direction means absorption process, downward direction means emission process. Okay, here interaction of atoms with radiation is so interaction of atoms with radiation. So that will be occurring two cases. One is the upward process, another one is the downward process. Okay, at equilibrium position, this upward transition as well as downward transition both are equal at equilibrium position. So these transition, there is the upward transition will be there. Upward transition occur when absorption process, when so these atoms are absorbs the radiation. So what happen? Upward transition will be takes place. Similarly, mm, so that radiation is interact with the second energy level, that is downward transition will be takes place, that is the emission process. I will explain you in emission process how it will be occur. So if you will take equilibrium position, so these transition rates are equal. First we will discuss about the upward transition. That process we will call it as stimulated absorption. So generally, so this process is absorption, but why we are calling here stimulated absorption means stimulated is nothing but so because of the external source, so this absorption is takes place. It's not a natural phenomena. So because of the external source, this stimulation process will occur, absorption process is occur. So that's why this absorption process we are calling it as stimulated absorption. Okay, now coming to the so that rate of absorption, that means rate of absorption is nothing but here how many electrons are will going to the excited state. That is depends on the rate of absorption. Okay, so here stimulated absorption rate depends on the, so here mainly there are two parameters will be there. So first one is the, see here, so the stimulated absorption rate depends on the number of atoms available in the lower energy state. That means it depends on the, so in lower energy state how many electrons will be there? There are n1 electrons will be there. Okay, so here we can pronounce it as a atoms or electrons. Okay, so whatever it will be, so here it will be depends on the number of atoms or number of electrons. That absorption process depends on the, so number of atoms available in a ground state. Okay, that is one, and another one. So and this absorption also depends on the, so photons, that means how many photons are interacting, how many, see here. So here some photons are incident on the ground state, that means here photon density. So here, so this depends on the photon density. Photon density means energy density, here number of photons into energy of the photon. Okay, so here mainly depends on the two parameter. So one is the n1, another one is the nh nu. NH nu is the energy density of the photons. Okay, that see here, that rate of absorption, rate of stimulated absorption is proportional to the N1, as well as so rate of stimulated absorption is proportional to the energy density, energy density of the photons. Energy density is here rho of nu. Here nu is the frequency, so rho of nu. Okay, so that's why that rate of absorption is equal to the, so n1 into rho of nu, n1 into rho of nu. There is a some constant will be there, that constant is b12. That constant is here b12. Why we are taking here 1 2 means, so here absorption is takes place in between the two energy levels. So those are the, so E1 energy level and E2 energy level. So in this process, that electron will move from, so first energy E1 level to E2 level. That's why we are taking that constant is, so 1 2. So electron is moving from, so first energy level ground state to, so second energy level excited state. Okay, that's why we are taking here B12. Constant is B12. Why we are taking here B means, so in case of stimulation process, this is the stimulation process we are taking here, so the constant is B. Okay, in spontaneous emission we are taking constant as A. In case of stimulated emission we are taking constant as B. Okay, so this is the B12 is the Einstein coefficient. So B12 is the Einstein coefficient for stimulated absorption. B12 is the Einstein coefficient for stimulated absorption. Okay, why we are taking 1 2 means, so here electron is jumping from, so energy level 1 to 2. Okay, so first state to second state. That's why we are taking here B12. So B is nothing but stimulated process. So this is the, in case of stimulated process, we are taking here constant as B. Okay, so this is the B1. Therefore, rate of absorption equal to B12 into N1 into rho of nu. Let us take, this is equation number 2. Now coming to the downward transition. So that absorption process is upward transition. Okay, now coming to the downward transition. In case of downward transition, there are two processes are there. So that means downward transition is nothing but emission process. In that emission process, there are two emissions will be there. So one is the spontaneous emission, another one is the stimulated emission. I already explained you. So what is the emission spontaneous emission? Spontaneous emission is nothing but without any external source. That electron coming to the ground state after completion of the its lifetime. Electron comes to the ground state automatically. So in this process, some radiation will be emitted. So this process we will call it as spontaneous emission. Okay, spontaneous emission. Okay, this spontaneous emission is so rate of spontaneous emission. That rate of spontaneous emission is depends on the only number of electrons in a excited state. It does not depends on the radiation. Okay, so it only depends on the number of electrons in a excited state. See here. Here E2 level, this is E1 level. So here how many number of atoms will be present? So because spontaneous emission means it is emitted automatically, so that emission will be occur automatically. So this is N2 here, number of electrons are N2. See here, so suppose here only one electron will be there means, so that rate of transition will be less. Suppose here, so 10 electrons will be there in so this N2 level means, so here, so that rate of transition is high. So that's why here it will be depends on rate of emission process will be depends on the, so number of electrons in a excited state. That's why, so rate of spontaneous emission is proportional to the N2. N2 is number of electrons in a second energy level or excited state. Okay, and here there is we are taking one more constant. So that constant is A21. Why we are taking 21 means that emission is occur, so from energy level 2 to 1. energy level 2 to 1. That's why we are taking here, so 2 1. Okay, electron is jumping from, so second energy level to, so first energy level. Okay, so first energy level, that's why we are taking here 2 1. So this process is spontaneous emission. That's why we are taking here constant A, constant A. Okay, so that's why we are taking here constant is A21. So this constant we will call it as Einstein coefficient of spontaneous emission. This A21 is called as, so Einstein coefficient of spontaneous emission. Okay, now another emission. So another emission is stimulated emission. Another emission is here stimulated emission. In that stimulated emission process, so stimulated emission process are, so that what is the definition of stimulated emission? So that stimulated emission is because of the external source, because of the external source, the external source trigger the excited electrons, external source triggers the excited electrons. So that's why here, so that stimulated emission is depends on the two parameters. So one is the, so N2, number of electrons in a excited state, number of electrons in a excited state. Those are number of electrons are here N2 electrons. Number of atoms are number of electrons in a excited state, that is the N2. Okay, and so energy density of the photon. So energy density of the photon also, it depends on the energy density of the photon. Okay, so if more energy density of photons will be there, means it triggers more electrons. So number of photons are high. If number of photons are high means, so it triggers so more electrons, more electrons. That's why stimulated emission rate, stimulated emission rate is proportional to the, so N2 as well as energy density rho into nu, energy density rho into nu. Okay, now that rate of transition is equal to N2 into rho of nu into, so there is another constant B21. Why we are taking here 21? So that means because the electron is jumping from second level to first level. That's why we are taking here 21. Why we are taking B here? So this is stimulated emission process. Stimulated process. That's why we are taking here B. Constant is B. So this is the B21. This constant is B21, and this constant is called as Einstein coefficient for stimulated emission, Einstein coefficient of stimulated emission. Okay, this is the B21. So this is the proportionality constant. All are the proportionality constants only here. So this constant here, Einstein coefficient of stimulated emission. Okay, now coming to the, already we discussed at equilibrium position. At equilibrium position, the upward and downward transition rates are must be equal. At equilibrium position, the upward transition rate is equal to the downward transition rate. Okay, so what is the upward transition rate? Absorption process. So absorption process is the rate of absorption. Rate of absorption is the upward transition. What is the rate of absorption here? N1 into rho of nu into B12, rho of nu into B12. This is the rate of absorption is equal to the rate of emission. So rate of emission, there are two emissions will be there. So one is the spontaneous emission, another one is the stimulated emission. So rate of emission is equal to the spontaneous emission plus stimulated emission. Rate of spontaneous emission plus rate of stimulated emission. Okay, that's why, so in case of rate of absorption is equal to the rate of emission. Okay, so this is the so B means this is the stimulated emission, this is the spontaneous emission. So this is the stimulated emission, so rate of stimulated emission plus rate of spontaneous emission. Okay, so at equilibrium position, rate of absorption equal to rate of emission. Now we will solve this equation. So for that, so what we are calculating, energy density rho of nu. Rho, for that what we are taking here also rho of nu will be there. I will bring this term this side. I will bring this term this side. So here I am taking common is rho of nu. Rho of nu is taking common. So remaining terms are, so N1 into B12 minus N2 into B21. Okay, so if you will send that side means, so N2 A21 by, so what is the remaining terms here? So only N2 A21 will be there. So that's why we are taking this side is common. That's why only remaining term is N2 A21. So if you send, so this multiplication term uh, after taking the common of, so rho of nu, so remaining term we are sending RHS side. RHS side. So that's why. So what happened here? That relation will be N2 into A21 by N1 into B12 minus N2 into B21. Okay. Let us take this is equation number 6. Okay. Now coming to the, okay. Here we are taking one more term is common in above equation. So what we are taking common means here N here N2 into, so because if you will take N2 common means N2 gets cancelled. That's why I am taking N2 into B21 is common. I am taking N2 into B21 is taking common. Okay, if you will take N2 into B21 common means what happened here? So there is no N2 term. That's why N1 by N2. Here there is no B21 term. That's why B12 by B21. Okay, so this total term is common. That's why it will become 1. Okay, see here. So I am taking here. So N2 gets cancelled. So remaining here. So B12 into B21 by into N1 by N2 minus 1. Okay, remaining term. This one is the remaining term. After solving the above equation, we will get rho of nu is equal to this one. Rho of nu is equal to this one. Okay, let us take this is equation number 7. Let us take this is equation number 7. Okay, according to the Boltzmann distribution law. According to the Boltzmann distribution law. So already I explained you in quantum mechanics. So how Boltzmann distribution law will works. Okay, so by using Boltzmann distribution law, we can explain the number of electrons will be present in a first level or second level or third level, like that. Okay, so here, so Ni, so Ni is the number of electrons in a ith state. Okay, see here. See here Ni means number of electrons in a, so ith energy level. Suppose we are taking here energy level, so I, so energy level I, so how many electrons will be present? So Ni is equal to N naught. N naught means ground state electrons into exponential of energy, exponential of Ei by kT minus Ei by kT. So kT is the thermal energy here, K is the Boltzmann constant, T is the temperature, Ei is the energy of the this excited state, energy of the so ith state. Suppose if you will take so second energy level, if you will take second energy level means N2 is equal to N naught into exponential of Ei my E2 by kT minus E2 by kT. If you will take N1, so this is we are taking this is E2 level now, so E2 level. So E2 level means here, so number of electrons are N2. N2 is equal to N naught into exponential of E minus E2 by kT. Similarly, we are taking ground state is here E1 state. E1 state. Okay. So E1 state, here number of electrons are N1. Number of electrons are N1. So here N1 is equal to N naught into exponential of minus E1 by kT. E1 by kT. Now energy difference between these two. Okay, so otherwise see energy difference between these two is E2 minus E1 na? Okay, E2 minus E1 equal to H nu. Okay, forgetting that's why what we are doing means, so I am just dividing here already we know that N1 and we know that N1 N2, and I am taking just ratio of N1 by N2. Okay, so N naught get cancelled because N naught is common term for N1 as well as N2. Okay, so remaining term is exponential of E2 minus E1 by kT. E2 minus E1 by kT. So okay, so just do it yourself. You can get. Okay, now E2 minus E1 is equal to H nu. H nu. Okay, energy difference between these two levels. Okay, therefore N1 by N2 is equal to exponential of H nu by kT. Okay, so these substitute this N1 by N2 value in equation number 7. in equation number 7. N1 by N2 is equal to exponential of h nu by kt. So instead of N1 by N2, I am substituting here exponential of h nu by kt. Exponential of h nu by kt. Here minus 1 will be there. Okay. Here also minus 1 will be there. Here not written. Okay. So minus 1 will be there. Just we are substituting instead of N1 by N2, we are substituting this value. Okay. So remaining as it is. Remaining as is. So from Planck's black body radiation, the density is given by rho of nu is equal to already. So we derived this equation. Density of energy states. Rho of nu is equal to 8 pi h nu cube by c cube into, so 1 by exponential of h nu by kt minus 1. 1 by exponential of h nu by kt minus 1. Let us take this is equation number 9, and above equation is 8. So compare equation 8 and 9. Compare equation 8 and 9. If you compare it, so what we are getting here? So this is the see here. So above term is 8 pi h nu by c cube. Okay. So what is the above term here? A21 by B21. Okay, A21 by B21 equal to 8 pi h nu cube by c cube. H nu cube by c cube. This is the A21 by B21. So if you compare these two terms here, so what is the multiplication of exponential? So multiplication of exponential is here B12 by B21. Here what is the multiplication of exponential? So there is multiplication of exponential is only 1. Okay, so that's why B12 by B21 is equal to 1. Therefore B12 is equal to B21. Okay, so this is the relation between the Einstein coefficients. This is the relation between the Einstein coefficients. That only we are proving here. So relation between the Einstein coefficients. Okay, that relation is equal to B12 is equal to B21, and A21 by B21 is equal to 8 pi h nu cube by c cube. Okay, this is the relation between the Einstein coefficients. Okay, so this is so already in your textbook it will be there. So just watch this. So if you will not understood means, so yeah, so take the screenshots of this. So I will remove all these whatever I written. So after that you will take the screenshots. Okay. So take the screenshots from here onwards. So this is the first page. And this is the second page here. Okay. And now this is the third page. The fourth page. Okay, this is the Einstein coefficient. So relation between the Einstein coefficient. This is the most important one. I will explain you once again briefly. Okay. See here. So there are interaction of radiation with matter. For explaining the interaction of radiation with matter, so Einstein proposed some equations. We are discussing about those coefficients. Okay, so for explaining those coefficients, we are taking here 3 parameters. So first one is the absorption, second one is the spontaneous emission, third one is the stimulated emission. Okay, for explaining the Einstein coefficients, we are taking those. So for that, so first of all, already we know that energy difference between we are taking two energy levels here. So E2 energy level and E1 energy level. Okay, E1 energy level and E2 energy level. So in E1 energy level, number of atoms are N1. E2 energy level, number of atoms are N2. So energy difference between those two levels is equal to h nu. Okay, now interaction of photon, how much of photons are interacting here? So that equal to rho of nu. Rho of nu is equal to nh nu. Interaction of radiation with matter. Rho of nu is equal to nh nu. Okay, that is the energy density of the photons. So energy density of the photons. Now coming to the upward transition. Upward transition, what happened here? In case of upward transition, that ground state is absorbs the energy. Ground state absorbs the energy. In that ground state, electrons will goes to the excited state. So that rate of absorption is depends on the two parameters. Those are number of atoms in a ground state as well as so energy density of the photon. Therefore rate of absorption equal to b12 into n1 into rho of nu. Okay, so this is the rate of absorption. Now downward transition. Coming to the downward transition. In case of downward transition, there are two processes will be there. So one is the spontaneous emission, and another one is the stimulated emission. First of all, spontaneous emission. In case of spontaneous emission, we are not using any external source. So that's why it's only depends on the rate of emission is only depends on the number of electrons in a second energy level. Number of electrons in a second energy level, E2 level. Okay, so number of electrons here, number of atoms are electrons. So that is N2. So rate of spontaneous emission is proportional to the N2. So there is a coefficient A21. So therefore rate of spontaneous emission equal to N2 into A21. Let us take this is equation number 3. Now coming to the stimulated emission. In case of stimulated emission, so it is depends on the rate of stimulated emission. Rate of stimulated emission is depends on the number of electrons in a excited state N2, as well as uh, one more parameter is, so that is proportional to rho of nu. So rate of emission is proportional to rho of nu. That means so it is the external source we are using. Okay, that's why it's also depends on the whatever external source we are using. Okay, that's why so rate of emission, stimulated emission is proportional to n2 into rho of nu into b21. Now coming to the at equilibrium position, rate of absorption is equal to the rate of emission. Okay, in that emission process there are two types of emissions will be there. So that is so stimulated emission and spontaneous emission. Okay, now we are taking here some common so I'm bringing this term this side. I'm taking common here. So n1 rho of nu is common. Remaining term is n1 into b12 minus n2 into b21. This is the remaining term. Okay, I am sending that here that term is multiplication term in LHS. If you send the term into the RHS, it will become in numerator. It will goes to the numerator. Okay, if you further simplify the above equation, rho of nu is equal, just I am taking common. So what is the I am taking common here? So b21 n2 into b21 is the I am taking common. N2 into b21 is the I am taking common. That's why here remaining term is 1. So here n1 by n2 will become. Okay, so this is the resultant equation. Now coming to the, so what we are doing, we have to calculate the what is the n1 by n2 value. n1 by n2 value. Okay, that n1 by n2 value I am taking, so by using Boltzmann distribution law. I am calculating here n1 by n2 value. N1 by n2, I am substituting this n1 by n2 in this equation. So your equation is wrong here. So 1 minute, I will edit this equation. So this one. Okay, so this is the right equation. So whatever we are taking here, this is the right equation. Okay, now we are substituting just n1 by n2 value above equation. Okay, if you substitute means here we will get, so this one. Okay, now coming to the according to Planck's radiation law. According to Planck's radiation law, so here rho of nu is equal to 8 pi h nu cube by c cube uh, by, so exponential of h nu by kt minus 1. Exponential of h nu by kt minus 1. Okay, so that if you compare equation number 8 and 9, if you compare equation number 8 and 9, we will get here what we will get. So this is the just, so 8 pi h nu cube by c cube, so that is gives to the a21 by b21. Okay, a21 by b21 equal to 8 pi h nu cube by c cube. So here, so exponential of h nu by kt, so this multiplication is just only 1, so that's why b12 by b21 equal to 1. So therefore b12 is equal to b21. This is the relation between the Einstein coefficients. Einstein coefficients. If you have any doubts on this equation, you can ask. Okay. I will download the attendance. If you have any doubts, you can ask. Otherwise, you can leave from the session.